7.4 video is brought to you by Lego Train Conductor. This guy's actually from the Santa Fe trains, which are worth some decent money. It's kind of funny. This dude's got a vest, and underneath his vest, he's got a zip-up something. Seems bad fashion sense, but really you shouldn't talk to me about fashion sense. All right, so in this section, we're going to look at the inverses of trigonometric functions. I already did kind of foreshadow this in 7.4 when I figured out what sine x equal to 1/2 was equal to. So first, let's just remind ourselves, what are functions? So if functions are like machines that take inputs and turn them into outputs, what does a function's inverse do? It takes outputs of the original function and turns them into inputs. All right, so consider a graph of a function. If there are sections of the domain where the function is only increasing, I'll give you a nice example. It's an exponential growth function. Or only decreasing, I'll give you another nice example. So this is, let's call this y equals b to the x. B is some number. And then this one is the nice, fantastic negative cubic. Y equals negative x cubed. So that's decreasing everywhere. This is increasing everywhere. What does it mean about its inverse? Well, first, in both of these cases, we'll say both functions are 1-to-1, if you recall that definition. And let me actually rewrite these in function notation. So let's do f of x, and let's do g of x for this one. So both functions are 1-to-1, which means both functions have inverses that are functions. You can always find an inverse relation. It's just that inverse relation, we want it to actually be a function. So what that means is, for any trig function, we have to define its inverse function by restricting it to a only increasing interval. Let me just say only increasing or decreasing interval. Let me show you what we mean by this. Let's just take the good old classic sine x function, and I'm just going to graph one period from 0 to 2 pi. So I need this, I'll cut that in half, there's a pi, cut those two in half, there's those. I know it bounces between -1 and 1. We start at 0, at pi halves, and this is 3 pi halves. We're going to hit 1, then back to 0, then down to -1, then back up to 1. So if you look at just this section, is this function 1-to-1? And your answer is like, fail, not 1-to-1, right there. Here's another place that fails, not 1-to-1. However, if I were to restrict my domain to just these values, so let me show that restriction. I'm going to restrict it to just pi halves to 3 pi halves. I would have a 1-to-1 function that would then have an inverse that itself was a function. So here it is. Swoop. That's more or less what it would look like if we restricted it to that domain. So that's going to be our goal, is figuring out what are the restrictions for each of the 6 trig functions that get us an interval over which the function is either only increasing. This interval I chose was just decreasing. And mathematicians are actually quite clever about how they choose them. So here it is. This is just a reminder, just like we think of square root of x as the inverse part of the function x squared, we must consider specific restrictions on the periodic trigonometric functions because they repeat values. So here are the restrictions. These are the restrictions of the original trig function. So we restrict sine to be negative pi halves to pi halves, so that when we take the inverse of it, we have a strictly increasing interval. Cosine is 0 to pi, and tangent, we restrict tangent to negative pi halves, not inclusively. That's because tangent of negative pi halves or pi halves is an asymptote. Here's what the graphs of these three trig functions look like. They are the sine and cosine and tangent functions reflected across the y equals x axis. And this is what you end up seeing. So let's see how these inverse functions work. By the way, notice the two different types of notation. Sine inverse, -1. This does not mean 1 over sine. It just says this is the inverse of sine. Or arc sine. Arc cosine, arc cotangent. So we want to figure out what's cosine inverse of 0. Well, this is really asking what's cosine of, boy, I'll put theta here. Cosine of what angle equals 0? Now notice we're doing these in radians. So using our memory of the unit circle, we note that this is a 0-degree radian. Did I just say degree? My Lanta. Okay, so this is a 0 radian measure, and the x-coordinate is 1, the y-coordinate is 0. Cosine refers to x-coordinates. So the angle that gets us this is both the 0 angle and the 2 pi angle. Now note our restrictions on the domain of cosine. It has to be all angles between 0 and pi. That means 2 pi is not a possibility for this answer. The only answer that's possible is pi. All right, let's do another one. So sine inverse of some angle, that's what we're asking. In other words, the outputs of these are angles, is equal to the negative square root of 3 over 2. Okay, let's note what the restriction on sine is. It can only be angle measures between negative pi halves and pi halves. So if I draw the unit circle of this, it's only those angles in the first and fourth quadrants. This is the first quadrant, this is the fourth quadrant. If you think carefully about this, that's a very logical decision, because all of the angles in the first quadrant have the same y values, in other words, the ordered pair in the unit circle, in the second quadrant. Likewise, all the angles in the fourth quadrant have the same values in the third quadrant. So what mathematicians did was say, let's take the sine function and let's restrict it to just these values, and now we'll have a function that's increasing everywhere, and this picks up every single possible output for the inverse trig function. So where do we get negative square root of 3 over 2 in our unit circle? Well, I know it's this one. This gives us the y value here. So this is negative square. Ooh, careful, careful, careful. This is positive 1/2 comma negative square root of 3 over 2 for the x and y coordinates. So what angle gets us that? Well, I know the angle up here is pi thirds. That gets us 1/2 comma square root of 3 over 2. So the angle down here, because of the way we've defined this, is going to be negative. All the angles from the first quadrant, just the opposite sign of them. So this answer is theta equals negative pi thirds. All right, next one. Okay, this is a tricky one. Cosecant inverse. We haven't even defined the inverse, the values for cosecant inverse. So let's turn this into sine. First note that what we're asking is cosecant of what angle equals 2, because this is equal to some sort of an angle, theta, we'll call it. We'll then note that cosecant, using a basic trig identity, is 1 over sine theta equals 2. Now I'll write 2 in a special way, 2 over 1. Because then when we have a fraction equal to a fraction, provided all values in the domain are valid, we can just flip this thing and we get sine theta equals 1/2. So flip this fraction, flip this fraction. Now notice we've introduced the possibility of extraneous solutions. Cosecant is undefined at particular values of theta. They are undefined at 0 and pi, and then any 2 pi of either of those values. So if we had a solution here, if an angle we found gave us 0 or 2 pi, it would not be a valid solution. In this case, it's totally okay because that's not going to happen. So let's flip to our unit circle now of sine. Now we're going to use the restrictions of our sine function again, just like in the previous one, in order for there to be an inverse. And we're going to note that sine of 1/2 occurs here. So the x-coordinate is √3/2. The y-coordinate is positive 1/2. That angle is pi sixths. So theta equals pi sixths.